Everybody, let's talk about gravitational potential energy in better detail than we did earlier. So at first we said, let's say you are holding some mass here above the ground. So what's the gravitational potential energy of this block? It is, gravitational potential energy is mg h for some height above what? Above some datum of your choice, which seems so arbitrary, right? Like what if you're like standing on a table and then the table's on the ground? Is the datum at the table or is it on the ground? What if you're in a 3-story building on the 3rd floor? Is the datum the 2nd floor? Is it the ground floor? And the building's on a hill and then the ocean's over here. Is it from here to sea level? It's so arbitrary. And it is. It's totally arbitrary. So now we know that this is based on saying that the weight is just mg, which is true near the surface of the Earth. But what if you're not? What if you're in space, far away from the Earth? So now we know that the gravitational force looks more like this. For some object here of mass 1, some object here mass 2, and then the distance between the two centers of mass, r. Now, I'll just tell you the answer. Gravitational potential energy looks like this. Okay, so you can just memorize that. So for the same situation, mass 1, mass 2, the distance between them, r, the gravitational potential energy is minus, there's a minus sign here, which is important, g, and again, g is that gravitational constant. Okay. Now, what does that mean? Where is the potential energy 0 now? Before it was at the datum, which is super arbitrary. Is there a value where this is 0? For sure, right? Look at this in the denominator. As r approaches infinity, then what happens? As r approaches infinity, then the gravitational potential energy approaches 0. Right? So let's say here's Earth. The gravitational potential energy is 0 when you are, like some block over here, infinity away. Like it has to be infinitely far away for the gravitational potential energy to be 0. And then what happens when you get closer? Does it get more or less? So when you think about that, as r gets larger, what happens? It's in the denominator, so this number gets smaller, but then there's a minus sign. So it becomes a smaller negative number. That is starting to sound confusing, which I think it's less confusing if you just graph it. Like here's gravitational potential energy as a function of r. So let's say when you are at the surface of the Earth, so if r is 6,380 kilometers, then you plug in the number here and you're going to get a negative number right over here. So if this here is the radius of the Earth, your one data point, it's going to be some negative value. And as r increases towards infinity, it'll look like this. Right? And then as r reaches infinity, as r approaches infinity, the gravitational potential energy approaches 0. So this is what it looks like. It's always negative, the gravitational potential energy, but then it approaches 0 as you get infinitely far away from the Earth. Okay, and that's if you're at the surface of the Earth or farther. When you're inside the surface of the Earth, that's another function which we can talk about at another time. I'll just tell the answer. It looks like this. See, so this is, here is, you're at the center of mass of the Earth. And like you dig a tunnel, and then from the center of the Earth to the surface of the Earth, the potential energy looks like this. And then as you get outside of the Earth, farther away, then it approaches zero like this. Okay. So that, I think, helps, right? Try and keep that picture in mind, because looking at this, it's like a smaller negative number that gets confusing to me personally. Okay, so now consider this. Like here's Earth, and you, like say you have a block over here. If you throw this block up in the air, what happens? It goes up and eventually falls back down. Right? So, no matter how fast you throw it, and then eventually, right, it'll come back and hit the ground again. So how fast would you need to throw something so that it never comes back, so that it can escape Earth's gravitational potential energy? Let's assume there's nothing else in the universe, because really, if you throw something fast enough, maybe it'll get caught by the sun's gravity or Jupiter's gravity. So let's say the Earth is the only planet, object, celestial body in the universe, and you throw this object. How fast do you need to throw it so it can escape? So in other words, that's called an escape velocity. How do we do that? So let's assume there's no non-conservative forces, so energy is conserved. Okay, so, and let's say you're starting at the surface of the Earth. Okay, so starting at the surface of the Earth. So what's the gravitational potential energy? Minus G, mass of the Earth, mass of whatever that thing is you're throwing, over R, and this will be the radius of the Earth. Okay, and then you're throwing it with some initial velocity, this much. I'll just call it initial. Okay, and then what happens if you throw it? Then there's gravitational potential energy afterwards, minus G, mass of the Earth, mass of the object, over some final distance, plus 1/2 mv final squared. Okay, so in order for you to escape Earth's gravitational potential energy, again, you have to be infinitely far away. So as this approaches infinity, this becomes zero. Okay, and then let's say we want the minimum amount to escape. So we don't want any extra. Like if you throw something fast enough, just barely, to escape Earth's gravitational potential energy, and then it just comes to a stop, then this is zero. If you throw it even faster, then this will start to become positive. So it escapes and it's still going at some speed. But if you throw it fast where it escapes and then where it's just enough for it to come to a stop, then this is zero. So this is the minimum velocity necessary to escape. Okay, so then let's solve for this. Just move this on the other side of the equation. Okay, and then this can cancel this, move the 2 over on that side. And square root. Okay, so this is, I'll just label it like this, escape velocity. So you have to throw something at least this fast for you to escape Earth's gravitational potential energy. And then infinitely far away, it'll have a zero velocity. If you throw it faster than this, then it'll escape, plus it'll have a little bit of extra, right, positive velocity. Okay, so there's one application, and then you can combine the two lessons from last time when we had orbital velocity. Right, so here's Earth. If you're like some satellite or something in orbit with some orbital velocity, and then you like hit some thrusters to go faster, then what happens? We talked about it last time. Then you'll change your path to be like a different shape ellipse, and then you hit your thrusters again, then you're like a different shape ellipse. So, but you're still caught in Earth's gravitational potential energy. So you would need to like kick in some thrusters so that you go faster than this, and then you escape Earth's what we call sphere of influence. Okay, so those are the applications. So let me know if you have any questions, and I'll see you on the next video.